We continue section 7.2, circuits and paths, talking about Hamiltonian paths. So definition and Hamiltonian circuits. So definition 7.2.4 says that a Hamiltonian circuit of a graph G is a simple circuit that involves every vertex of G. And we want to address a few issues. First one is, why would it be relevant? Why would we learn that? And then when can we expect a graph to have some Hamiltonian circuit and when not? And of course, if this is not a circuit, if it's just a path satisfying all this, then we'll say that that's Hamiltonian path. So, so here's a nice example. 723. Goal is to label, I got it from the Epps book actually, Epps book that we use as a reference. Goal is to label 2 to the n sectors of a DVD. So that each 2 neighboring sectors have only 1 digit different. What are the practical reasons for that? Then if we have the error in 1 digit, which happens, then we're not going to miss completely like going to the opposite side of the disk. We will be more or less in the same vicinity, and that would have less consequence. So if that's the case, then how can we really make it sure that we will include all 2 to the n, all 2 to the n sectors that would satisfy this? So here's the nice representation of that problem. You generally label, so this would be the case when we have 2 to the 4th. So this is the case n equals 4. So we have 2 to the 4, which is 16 of these sectors. And then what we did, we just labeled, this is like 4-dimensional cube. How did we make it? We took 3-dimensional cube, this is the black one, and then we took 3-dimensional cube, blue one, and then we connected them with the green connectors, and that's really was this 2D representation of the 4-dimensional cube. And then each of the vertices is labeled. So this one is, for example, 1, 0, 0, 0. So this one would be 1, 0, 1, 0, and so on. So then, really, we in that case, if we label all the vertices this way, then the neighboring vertices differ only by 1 digit, because when you go from one vertex to the other, you only change one of the digits. And then what? The question is, how do we line them up so that we really have the neighbors lined up next to each other? So here is basically what we want. We want a rule that would tell us how to start and who to put next and so on, so that each of them is listed and that we don't run out of space. And here is the idea. We actually want exactly Hamiltonian path. Actually, it doesn't have to be a circuit. So what can we do? Generally we start here, so this one does have Hamiltonian, but this is just improvising. I'm not telling you how we can do that. You generally start from one corner and then cover one cube, let's say like this. Then what do we do here? We go up. So we finish the bottom, we go up, and then we cover in the, so we go up, and then we cover the top one. So we were here, we covered this, we covered this, and we covered this. So generally by doing this, we really visited all the vertices in the little. So I was here, I was here, I was here, and now I'm here. So everything is covered in the little cube. So I put all these sectors next to each other as first 8 sectors. Then what do? We go across the big cube through one of the connectors, and then we actually cover the big cube in the opposite direction. So whatever I did here, I did on its twin. Then this one goes to the right, I go to the left. This one goes down, this one will go up. This one went up, I go down. And then when I get down on this one, it was coming left, I'll go right. Then I'll go down here, and then I'll go left, and I will end up here. So all these vertices were visited this, 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 and then if I want, I don't need that, I just need Hamiltonian path because I don't want 17th one, but here is the 16th one. So if you order them like this, since each of them are neighbors, then you would get all of them different by just one digit. All right, here's another. So just a couple of nice applications in the beginning. And for example, here is a nice, very nice application that doesn't have really, it's not so easy to set up the problem. I like this picture so much that I feel bad to erase it. So what would that be? Example 724. We are remodeling 5 apartments, and these numbers here represent the number of hours needed to do the painting and carpeting on both of them. There's one carpeting and one painting. So where the first number represents painting. Okay, yes, painting is done first. So D12.4 and E7.7. So first number is painting, second number is carpeting. So so here's your here are the standard constraints. Each apart. So we have just 2 teams, one for painting, one for carpeting. So we would like to finish all 5 of them as in the quickest amount of time. Following a couple of constraints, that means team finishes one before it can go to the other, and also in none of the apartments you can do carpeting before painting. So generally painting has always to be done first, and then you want to minimize the amount of waiting. And then, we actually developed a criterion when is it better to do one than the other. So we say the following, so if we do AB ahead of CD in our decision, then what? The total amount of time would be A plus maximum BC plus D. Why is that? Because you need to do first one for painting, and then who's next? Whatever takes longer. So generally, either you need to wait B, so to do D at the end, you need to finish both things. So carpenters need to finish first apartment. Even if you do quick painting in the second one, you still need to wait for those guys, or the other way around. If these guys are done, then they wait for you for painting. So whatever maximum BC is in D. And then the same way CD is less than AB by analogy, if what? C plus maximum of middle numbers, which is maximum AD plus B. So the question is, when is this less than this? And then there is a nice trick. Generally, what would that be? The nice trick is that actually maximum plus minimum. We know that max of BC plus min of BC is just B plus C. because one of them is max, one of them is min, so we don't care which one because of commutative law. So max plus min is b plus c. So generally we can replace max with b plus c minus min. So I get the following: a plus b plus c minus min bc plus d should be less than c plus, this would be what, a plus d minus min ad, for the same reason, plus b. Now a plus b plus c plus d are everywhere, so they cancel each other out. And then if we get minimum on the left side, we get the following criterion: minimum of AD is less than minimum of BC. So generally, you order them so that, in such a way, that minimum outside is less than minimum inside. So for example, and then we record the decisions according to the, and we record that as a graph. So this is AD. Here is C, here is D, here is E. So generally what? We take minimum. So minimum outside is 3, minimum inside is 6. So I'll do A before B. So I put an arrow that A is before B. What about A before C? The same thing, minimum is 3. So these 3 is obviously killing everyone. So A is better than everybody else. So A for sure has to be first. And then the same way, I'm not gonna waste time. So C will be done before B, and then everybody before D looks like it according to my arrows with this test. And then so everybody before D, what's comparison B and E? B before E. And then what? We want one specific order, so we want actually in this graph, what about E and C? E and C, C is beating E. So generally what? Then we can make a Hamiltonian graph. Here it is. A into C, C into B, B into E, and E into D. So if we do this order, A, C, B, E, D, we are sure that we'll minimize the time. I don't know if I calculated it. I didn't, but that's what it is. And then what? So natural question comes: is it? Are we sure that how were we sure that Hamiltonian path exists? We were lucky here that Hamiltonian path exists, although on this one we see quite many of those arrows. So generally, it was very likely that we'll have Hamiltonian degree. So now, after these few examples that I both like a lot, because they are really realistic and have powerful ideas, let's address that issue. If when we see a graph, how do we know if Hamiltonian path or circuit exists? And then can we make it in a specific case, and can we predict it according to some properties? So first, just by trial and error, so 725. So 725, like this, you already have it in our notes. So it looks like this, there's like parallelogram here, there is like rectangle here, triangle down. Shapes are really completely irrelevant. You can draw however you want as long as connections are there. So here is A, H, F, I, J, G, I, D, F, this is B, and this is C. So generally if you want, so what? In this one, the question is, can we make a Hamiltonian path? And then here it is. Be careful when you run upon a Hamiltonian path. These are very sensitive. Why? Because they have only 2 edges. That means once you come, then you have only one way to leave. So when that happens, for example, or let me start with A, for no good reason. But I'll go AH, then HF. Here you have to be very careful from F actually to cover I first. Why? Because I has only two options to be visited. So if you don't visit it now, the moment when you get into J, I stuck, because if you get in I, you have no way out. So generally when I have something like this, I will definitely go through I. So generally the idea is always visit the place with the smallest degree, otherwise that could be a trouble later on. So what do we do here? Going to J, J goes into G, and then we cannot go here, we don't care, we don't need to visit all the edges, so we go here, we visit I, so we visit all these nodes. Then what? We visit D, going this way, D we visit B, going this way, and then we visit C, go this way. Here it is, we visited all of them, and we visited only once, so this is the Hamiltonian path. So starts here, and ends here. All right, so, so here it is. We were just lucky to get Hamiltonian path, and then the question is, can we make it, because it's not a circuit, we started with A and then it did D, the question is, does it have a Hamiltonian circuit? So generally, we will try, I'd like to show you how do we argue that the circuit does not exist. So generally we want to find some properties that will force that circuit not to exist. So let's say the following. I can start, since circuit goes all the way around, doesn't matter where does it start. So I can start my analysis. Let us start with i's. Okay. And then again, direction really doesn't matter. We can reverse it. So we will go. We went A, H, F. Okay, so I must be, so it has two options. So one coming, one receiving. However you go, as I said, we can reverse it. So definitely, if that circuit exists, we are arguing by contradiction. One edge must go through F, either this way or that way. As I said, we can reverse it, so I'll think of it this way. So from I, you must go to F. Circuit must have connection. Okay, no, I said what? I is receiving. Doesn't matter, analysis can go the other way around. So generally I, let's say, is getting it from the connection from I, and it has to go to J. You cannot avoid that in this direction or the other. And then what? H must be included, because if you don't include H, if you go later on, you will be stuck at H. So there is no way for you to get there the other way around. So you must have some. So however you make a circuit in one or the other direction, it must have H, F, I, J. And then what? H has only can get from A. So generally, this is forced because of those elements of degree 2. No matter how we would choose that circuit, it must have, as I said, in one or the other direction, it must have A, H, F, I, J. So we didn't assume anything special. And then what? Degree of C. So these degrees 2 were crucial. Since degree of C is 2, as I said, you must go through it, otherwise you will be stuck at the end and you cannot get back to A. Actually, we decided that start of the analysis is A. So we have to go through C. And then once you go through C, you have to go to B. And then what happens? We cannot visit D. Why? Because if we visit D, that's our last chance to get back to A. So generally we have to go to I. But then again, but that's it. This is contradiction. No, we are not even allowed to go to I. We already visited I. So A, H, F. No, this is labeled differently. That's E. So that's E and I. So what? If we go to E, now we cannot go to D because G would not be visited, but if we go to G, we get stuck because there's no way to go because all the neighbors are already covered. If we go to D with the intention to get to A, G will be uncovered, so we get the contradiction. So generally just, as I said, crucial in this analysis was that we had quite many vertices of degree 2, and they, when you arrive to their neighborhood, you cannot neglect them. You have to go through them because that's their last chance to kind of get the edge that comes and edge that moves. All right, so we saw an example where we would have and we wouldn't have the path. So here's the theorem. That's a nice theorem of OR, 7.2.4, theorem of OR, that says basically if G is a simple graph, with n vertices, n greater or equal to 3, such that d of u plus d of v is greater or equal to n for every pair of vertices. Then G has a Hamiltonian circuit. And it's an interesting proof. I'm not going to ask you that neither on the quiz or on the exam, but since basically what? To the contrast from Euler circuits and paths, where we had very clear criterion to see if they exist or not, for Hamiltonian paths and circuits, there is no general criterion that would tell you that. So this is just a special case that tells you basically this is just sufficient conditions. So be careful, don't use this wrongly. So this is sufficient condition if you have heavily loaded graph, because this says that really heavy degree elements that generally have very heavy degrees. Then if that happens, then Hamiltonian is guaranteed. If that doesn't happen, we just don't know. Don't assume now when that would be the wrong way to use logic. If a graph doesn't satisfy this, then it doesn't have Hamiltonian. No. For example, this one has so when you take I, H, and C, their sum of degrees is just 4, so it doesn't satisfy this, but it still has Hamiltonian path. Okay, this is for circuit, but it's easy to make examples of Hamiltonian of graphs that do not satisfy this, but still have Hamiltonian circuit. So this is just sufficient condition, and it's interesting to see the proof. So proof goes like this: assume that that a G is the minimal graph. So let's argue by contradiction. So we assume that the graph satisfies this, but doesn't have a Hamiltonian circle. So then assume that G is the minimal graph, satisfying the condition. But not having Hamiltonian circuit. What does that mean actually? That means if it's minimal, that means if we just add one edge, it will have Hamiltonian circuits. Otherwise we would keep cutting and get smaller and smaller graphs. And then what? So if this one doesn't have Hamiltonian circuit, that means if we add just one edge, G prime would have Hamiltonian circuit. But now we go backwards, we cut that edge, and there is a theorem that we proved in the first part of the lecture, where we cutting one edge from a circuit leaves a Hamiltonian path. Because it's Hamiltonian, we don't change nodes visited, just number of edges, leaves the Hamiltonian path. So without loss of generality, we can assume that the G has Hamiltonian path. So one short of having Hamiltonian circle actually guarantees the existence of Hamiltonian path. So here it is, let this be Hamiltonian path. So we have graph here, G, with all that structure, whatever that is. And then when you line them up, you have like this, V1, V2, V3, V4, V5, V6, V7, V8, V9, and let's say, and so on, Vn is the last one. And they are all connected. Then what do we do? We say the following, look at the V1 wherever it is, and look at all those. So let me label the degrees. So let's say the degree of V1 is K, degree of Vn is L, and according to assumption, K plus L is greater than or equal to N, which is the number, so size of G's and vertices. And then what? We look at all those in the graph that are connected with V1, and there are K of them, and I will call them T1, T2 to Tk. And I will identify them here. So let's say this V4 is actually T1, and let's say that this is T2. Okay. Then I look at the members in the path preceding them. So before T1, I'll call this S1. Before this one, I'll call this S2. And so on. I have S1, S2, and Sk. And here is the crucial thing where we need our theorem. V1 must be connected with one of the S's. So if I have some S2, S1, Sk, then Vn, wherever it is in the graph in general, must be connected with one of them. Why is that? Because degree of a Vn is L. And we know that K plus L is greater than or equal N. So if he's connected with L, then what? Number of those he can miss at most K vertices. He's connected with L, and then total is N, so those that he missed is less than or equal N minus L, so he misses at most K vertices. But that's exactly S1 to Sk, but there is one more thing, and that is Vn is also not connected to itself, so generally among S's, Vn misses at most K minus 1 S's. So that means Vn is connected with one of those S's. So there is an edge between one of Si's, green Si, and the N. And then what are we gonna do? We're gonna make a circuit like this. We'll let this be that S, or let that Si be this one. So here's what we do. We start with V1, go all the way until we reach that Si. Then from Si we jump to Vn because there is a connection between them, and then we reverse the path backwards. So we go backwards, we go, until we reach the neighbor of a Vi, which is T. And that T, by assumption, is connected with V1, so from there we just jump there, and we get back to V1. So what will happen, we take half of the path in the normal direction, then we do the kind of shortcut here. Then we use second half backwards, but then one step before RV7, when we are guaranteed connection with V1, and here is a circuit. And this is a contradiction because we assume that there is no circuit. So assumption that this type of graph doesn't have a circuit gave us contradiction, and that proves our statement. And then special case of this theorem is Dirac's theorem that says what? So theorem or corollary. Dirac. This is not Saint Paul Dirac from quantum theory and from the differential equation course. This is his stepson actually. So, so what is the theorem says? If degree of every vertex V is greater or equal to n half in a graph that has n vertices, then G has Hamiltonian path. And that's trivially true. Why? Because if everybody is bigger than n half, then when you have k plus L for any two vertices, that's bigger than n half plus n half. That's equal to n. So the original Bohr's theorem is more general. It doesn't insist on every member being heavily loaded, but just whenever one member is weak with degree, the others must compensate that. So we have a little more flexibility. And finally, the famous comment about traveling salesman problem. Salesman. So what is that problem? Problem is that we have a graph where we have not only edges, but edges are weighted. We will see that in section 7.5. So there are some edges, some connections. So these are sickies, A1, A2, A3, A4, and A5, and there are connections between them. And then you want to make a path or a circle, depends on the formulation, where you visit all, and then there are some distances here, 17, 35, 19, 27, 3, 15. So you want, a salesman wants to visit all of them, covering the shortest distance possible. So shortest distance, Hamiltonian path. So theoretically, this problem is very simple because you just calculate all the Hamiltonian paths and then among them compare them according to the length of the road, and then you get the best solution. But generally, for practical purposes, this is not an efficient algorithm, and that's why this problem is considered still open. So we are still looking for an algorithm that would give us a good strategy for large number of cities and large amount of possible edges and distances to give us a way to find that path in some shorter amount of time, like polynomial amount of time.